All right, this is lesson one, limits and continuity, part one, limits and continuity, part one. It's the first lesson of a series of 12 that are meant to essentially just go over all the major topics of Calc A for the sake of review. The videos are optional. They're recommended, especially if you know you don't remember every little thing from Calc A. However, you could also pick and choose. If there are topics that you're sure you are 100% comfortable with, you could skip those videos and just watch the ones where you need a little bit of a refresh. Quick note about the videos, as I go through these slides, you'll see that the answers are already filled out. The reason I'm doing that is because it makes the video go just much quicker to record. So I don't have to be constantly writing things out, especially while I'm talking, in which case my handwriting gets super bad anyway. So if you don't like the spoilers of the answers being there, I would recommend get the blank copies of these slides off of Schoology first. You can try them on your own, and you can either check the answer key on Schoology, or you could turn to the video for the parts for which you want more explanation. All right, let's get to it here. This first slide, what even is this class? What is calculus? Excuse me, real quick intro to that. Everyone has taken algebra already, probably a couple times. Algebra and calculus both deal with functions. And of course, with functions, I'm talking about something like a definition for y in terms of x, like y equals x squared, y equals e to the x, y equals natural log of x. These things are functions. In algebra, we learned about the properties of the most common functions, but there was an emphasis on what's happening at specific locations, or for specific values of x, what y value do you get, or at what x values do you have a zero in your function, things like that. In calculus, the emphasis is now on what happens as quantities are changing. Now, having said that, calculus does rely heavily on algebra. In fact, I've had students in the past that are pretty competent with newer calculus concepts, but the algebra is what gets them. If you don't remember what a log is, if you don't remember, a lot of the trig identities and the unit circle, that's where you might run into trouble. So make sure that you're familiar with things on this list. And if you're not, that's not the end of the world. You just have to be willing to spend a little time on your own consulting notes from either previous years or from the internet. Okay, so yeah, on the left here, we see a list of the common classifications of functions that you're going to see throughout the year. You definitely want to be pretty comfortable with. The right has some other things that aren't specifically functions necessarily, but still concepts that are important. The most important thing over here by far, I would say, is the trig identities in the unit circle. All right, those things start coming up pretty regularly, pretty soon. So you want to be good there. All right, on with the main event here. I'm gonna go down to page, I guess this is page 3, example 1.1. Okay, so we're looking at limits off of a graph. There's also some algebra questions mixed in here. So things like, what is the domain of a function? Well, I'm just looking at what are the possible x values that we can plug in to this function. Just looking at the graph here, I've got this function that kind of loops up and around and does some interesting things at 5 and 7, but the leftmost x value appears to be at 0. The rightmost, well, there really isn't a rightmost because we have the arrow going to infinity. So your domain is 0 to infinity, 0 included. Range is a representation of the outputs that we get. What are the possible y values that we get back in this function? It looks like the lowest value is at 1, but we do have an open circle. So for that reason, we're not including 1. And then the highest defined value is 8. So our range is from 1 to 8, 8 included. At what x values is f of x undefined? Well, we don't have anything that appears to be defined to the left of 0, so I'll say x less than 0. Algebra question, what is the value of f of x when x equals 0? Or literally when you plug in a 0, what do you get back? Well, our y value is 3. What seems to be happening to our function f of x as x begins to increase from 0? So as x gets bigger, we could travel along the curve and try to describe what we're seeing. And of course, the informal quick answer is that The values of f of x appear to be increasing, at least at first. As x gets closer to 3 from either side, what value does f of x approach? So now we're getting into more calculus question. As we approach 3, as x is changing, what is f of x doing? Well, whether you come in from the left side or from the right side, the y values are getting closer, closer, closer to 8. So this is our first real indication of the concept of a limit. What is f of x doing as we approach a certain x value? Next question is back to an algebra question. What is the actual defined value of the function at 3? Answer is also 8. Okay, these two questions that we just talked about have the same answer, but they're not the same question. There can sometimes seem to be a subtle difference there. What's happening at a location versus what's happening as we approach a location. Sometimes it's the same, sometimes it's not. In fact, as x gets closer to 5 from either side, what is f of x approaching? Well, as I get closer to 5 without actually getting there, it looks like the y values are approaching 1. Hence my answer. But then the actual defined value, f of 5, is this isolated floating point. So I would say a y value of 3. Those are not the same answer, which proves that these are not the same question. Okay. Approaching 7. As x gets closer to 7 from the left and from the right, what is f of x doing? From the left, let's see. It looks like we're getting closer and closer to y equals 3. We don't actually hit y equals 3, but that's not what the question's asking. It's about what's happening when we approach. As x gets closer to 7 from the right, there doesn't seem to be much change happening at all in the y value, so we just say 6. The actual f of 7 is 6 because that's where I see a closed circle. So limits are more formally defined on the next page. Okay, this is what we were just looking at with our graph example. A y value that a function approaches, not necessarily the same thing as what happens when we get there, but what are we approaching as x approaches a specific value from both directions. That's an important part of the definition. A standard limit question assumes you're looking from both directions. If there is not a single value that's approached from both sides, if you're getting different answers from either side, that's when we say a limit does not exist. All right. However, we are allowed to explore one-sided limits. We can exclusively say we're only going to look from the left side, or we're only going to look from the right side. We've got notations to represent left and right, little minus and plus signs. So you could have a limit that does not exist, and yet the one-sided limits do exist. Okay. Properties of limits tucked into the bottom here of page 4 basically just says if you have a limit of some composition of functions, well, in this case, it's specifically a plus minus multiplier divide operator between two functions, you are allowed to evaluate the limit of the functions separately and then just apply that same operator afterwards, as long as you're not getting any division by 0, as long as all 3 of the limits in that equation are real numbers. All right. You can pause the video at any time to read over some of this stuff or process it, but I'm just going to keep going here to make the runtime as short as possible. Moving on to example 1.2, estimating limits from a table. This is something that could come up occasionally. We have a function mentioned here, but for whatever reason, we're not necessarily going to use that equation directly. Instead, we're looking at values already plugged in for us in this table. And just using the evidence in front of us, can we figure out what y value is f approaching as x approaches 2 from the left? So the strategy here would be to look at x values, notice where they're getting closer to 2 from the left. I'm looking down this first column here. These numbers are getting closer and closer and closer to 2. So if I look for a pattern in the f of x values or the y values here, what do they seem to be approaching? They seem to be getting really, really close to 8. What y value is f of x approaching as x approaches 2 from the right? Similar thing, just going from the other direction. Here I see values as I move up this second column. That's where X is getting closer to 2. Meanwhile, the Y values are also getting closer to 8. So because I have the same answers here from the left and right, I can say that in general, yes, the limit of f of x as x approaches 2 does exist, and it is equal to those very same two answers we just found. Off to the right here, some instructions you can read on your own if you are interested in, coming up with a table like this on your own. If you didn't have one provided, there are quick ways to generate a bunch of different f of x values using a TI-89. But we're going to get back to graph. We're in fact revisiting the example from earlier, but this time we're going to apply our limit notation. Okay, so we saw this limit notation first show up in the definition a couple of pages ago. So instead of writing out in sentence form, what is the limit of f of x as x goes to 3? Instead, we could just package it up in this nice notation here. This is saying, okay, what y value are we approaching as x gets close to 3 from both sides? Of course, we know the answer is 8. Likewise, if we approached 5 from both sides, in both cases, we seem to be approaching 1. It doesn't matter that we never actually hit a y value of 1. That's not what a limit question is about. That's just about what we're approaching. X going to 7, as you approach from either side, you are not approaching the same y value. This is the case where we say the limit does not exist. However, we could modify our notation to specifically ask about left and right side, and in those cases, we get answers. So, is the statement here true or false? Of course, you can see the answer. It's sometimes true, but sometimes false. That question is, will a limit approaching a certain x value always be equal to the actual defined function value there? And not always. Sometimes it works. At x equals 3, y is 8, and the limit was also 8. In that case, these two things are the same. It actually has to do with continuity. But in cases where your function is not continuous, like at x equals 5, the limit does not match the actual defined value. Okay, moving on. Example 1.4. On this page, there was some practice with just graphing piecewise functions. It's a skill we should be pretty comfortable with at this point, but to save time, I'll just kind of move along with the calculus questions. I got to assume that you all are able to graph these things on your own, or if not, you can look at some notes and practice. So yeah, here's the correct graph for part A. Once we have it there, a lot of these questions should be pretty easy. Domain and range, what x values are we using, what y values do we get back? Notice here that there are no y values between 3 and 4 that actually exist. So I've got interval notation there. At what x values in between 0 and 5 does the limit not exist? There's only one place where that is occurring, where we don't have a limit existing, same from both sides. That's at x equals 3. At x equals 5, that's the only place from 0 to 5 where we have only a left side limit existing, and then on the other end, only the right side exists at x equals 0. Then part B, some more practice. If you need to pause and, make the graph, if that's something you want to practice, you could always do that. But here's the finished copy. The first row of limit questions is once again highlighting that a left-sided limit can exist, a right-sided limit can exist, but if those values aren't the same number, then in general, the limit as we approach -1 does not exist. And then just a few more questions here to kind of test yourself if you're interested. But we're going to get away from the graphical approaches now. We're going to start looking at what's called evaluating limits analytically. I'm down on the next page now there. In fact, let me scroll that up. And this is where you don't have a graph in front of you. You don't have a table. Instead, you might just have a function itself based off of just the written function. Can we evaluate limits at certain x values? And there are a few different strategies for this depending on the conditions of the equation that you're dealing with. So for now, we're just going to start with the easiest case. And that's, of course, the case where we're dealing with continuous functions, or at least functions that are continuous at the x value that we're interested in. Okay. Well, and we'll talk more about continuous, I think, in another video, but informally, it's basically if you can trace a curve without picking up your pen or pencil or stylus, then then it's continuous throughout the interval that you looked at. And what's really nice about that for us is that continuity is exactly in line with the situations where the limit is equal to the actual function value itself. If you're looking at a continuous piece of a curve, then limit of f of x as x goes to c is equal to f of c. What's really nice about that for you is it means if you know your function is continuous, then to solve these limit questions, all you need to do is take the x value that we're approaching and just plug it in to the function itself. And basically, if you can plug this number in and get back a real answer, that means it was continuous and you're good to go. So that's usually the first thing to try when you're evaluating limits analytically is, can I just plug this number in and get back a result? If so, that's my answer. So we plug a 0 in to x squared minus 4x plus 1, we get back a 1. That's the limit. It happens to also be the actual f of 0, but we're more interested in the limit right now. Can I successfully plug a -1 in here and get something back? Yes, I can. Ooh, here's the trig showing up. Can we successfully plug in a 5? Yes, but I think the bigger question is, do you remember what the tangent of 5 pi over 4 is without a calculator? If you're not feeling comfortable with that, well, it's something you got to study. But of course, the answer is 1. Same thing with cosine and even logs. If we want to plug a 0 in, did we recognize that cosine of 0 is 1? And then after that, do we recognize that natural log of 1 is 0? Last couple examples, I don't see an x anywhere in the function itself. This is a constant function. No matter what x is, y is just equal to 8. That's not a problem for us because no matter what x value we approach, we're always approaching a y value of 8. It never goes anywhere else. So even if I don't tell you specifically what x value we're approaching, we know the answer is going to be 8. All right, is this coming back to you guys? Remembering all this stuff from last year? Let's crank it up a notch here. I've got some piecewise examples on the next couple pages. These can be a little trickier, but still doable. Okay, so the problem with piecewise functions is we can't necessarily tell instantly whether or not these pieces connect to each other. And that's important to look at because if the pieces connect, you have continuity, okay? And that makes things generally pretty easy for us. If these pieces don't connect, well, then you're not gonna have a limit existing at that boundary between the two different pieces because, well, you'll be approaching different y values from either side, okay? So that's what we're looking for here. Ultimately, we want to answer the question, is continuity necessary for a limit to exist? A lot of times your limit doesn't exist when they don't connect, but there are actually cases where, there's cases where you still have the limit exist actually. So I did put no there, but we'll see why in a second. I'm getting ahead of myself. Let's start with this g of x here, okay? Now, a couple of these limit questions here, x approaching 0, x approaching 3, those are just there to remind you that if your x value is very solidly located on a specific piece, you don't even have to look at what the other piece is doing. Like 0 is less than or equal to 2, so we only want to look at -3x plus 1. Okay, the x minus 7 portion has nothing to do with this particular question. I just plug a 0 into the first piece, I get back an answer. Likewise, down here, x approaching 3. Well, 3 is definitely bigger than 2, so I'm only interested in plugging that into the second piece. But limits involving 2, whether it's from the left, right, or just in general, those are the interesting questions. This is where you have to actually check both sides. Okay. So even though this thing is asking me about x approaching 2 in general, I'm going to separately look at the left and the right. So what that means is I'm going to have to plug x equals 2 into both pieces. What's happening from the left, what's happening from the right. Okay, if I plug a 2 into this first piece, I get back a -5. If I plug a 2 into the second piece, I also get back a -5. That's really, really good news because that means the pieces are actually connecting at x equals 2 and the overall limit itself is -5. All of that changes for h of x. In fact, the only thing I really changed in this function is what used to be a 7 is now a 6, but that's a big change because now your limit from the left is still -5, but limit from the right is -4. Those numbers are different. So the overall limit as x approaches 2 is now does not exist. Okay. So h of x was not continuous there. Now, the real weird one is this f of x. Excuse me. It's got 3 pieces. Okay. As you approach x equals 2, coming in from the left puts you on the first piece. All the values to the left of 2, I want to follow this rule. I get back a limit of -5. Coming in from the right, I'm interested in this last piece. I also get -5. Because those match, I can confidently say the overall limit is -5. However, I didn't actually have continuity because we have this separate middle piece that defines what this function does precisely at 2. It's a +5. If you were to graph this, you'd see 2 pieces, and this isn't the exact correct graph, but you know, you'd see something like this, open circle, and then maybe a point floating somewhere else up there. That's what that would look like. All right, so be really, really careful with piecewise. We've got another piecewise example on the next page. Just kind of flips things around a little bit. Here we have 2 pieces. There's an unknown value a in there. We're supposed to figure out what it is, and we're supposed to assume that the limit will exist. Okay. Strategy here is, well, based on what we saw on the previous page, if the limit is going to exist, we would need these 2 pieces to end up equaling the same value precisely when you plug a 3 into either one, right? So if I plug a 3 into each of these pieces, right, I get a 12 minus a, I get a -9 plus 3a plus 1. I don't know what a is yet, but I know that those 2 expressions have to equal each other. So we'll set them equal to each other. And in that way, you can figure out what this a value would have had to be to make this thing work out as described here. All right, example 1.8, we are switching gears a little bit here. You know what, this ties back into the limit properties that were discussed, I think, back on page 3. Here are some limit information that's just given. And then we see some various compositions of functions here. Okay, you know, as x approaches 2, what's the limit of 4f minus g? Well, you're allowed to just take 4 times the limit of f minus the limit of g. Both of those limits I just mentioned are given. And then just work through basically the operations there. 4 times 3 minus 5. Here's another one. If I have g times h times x as x approaches 2. So if x is approaching 2, I just plug a 2 in here. So 2 times g of 2 times h of 2, or rather 2 times the limit of g times the limit of h as g and h both approach 2. Whichever way you think about it, it turns into 2 times 5 times 6. Okay, and then of course, one more example there you could look at on your own. We are getting near the end here, I think. A couple more pages. And what we're going to talk about on the next page, evaluating limits analytically, but the not so easy ones. What happens if I have a function where I can't just plug in a value and get it to work? All right. And even for non-continuous functions, there are several different cases we'll look at. So we're going to start today with just the ones that are called point or removable discontinuity. Okay. I'm not going to read through all this slide. There's a lot of words here. You could pause it and look at it on your own. Basically, the gist of it is a removable discontinuity is one where typically the function when written out is such that there's something that kind of cancels out. You see the x minus 1 on the top and bottom here of this function on the bottom right. And it's interesting because this function, if you graph it, it looks really similar to just y equals x plus 1. You have to be careful though, because you cannot claim these are the same. Yes, they're the same for most values of x, but they're not the same at x equals 1. The one on the left is defined. The one on the right technically is not. You cannot plug a 1 into this. Okay, just because x minus 1 might cancel for most numbers we plug in, it doesn't really work that way if x equals 1. You do end up with a 0 in a denominator. Okay, so the difference graphically is just a single point of discontinuity. Okay, but what's really nice about these functions with limits is that, if I'm talking about a limit as I approach this discontinuity, I can cancel these like factors out, because limits are all about what happens as we approach an x value, not what necessarily happens right when I get there. Okay, so long story short, if you have an expression, and I'll start transitioning down to the next page. If you have an expression where you try to plug in your given x value and it doesn't work out, see if you can factor that thing and get some cancellation, because if you can, then the answer you end up with will be a valid answer for a limit, even if it wasn't a valid answer for the algebra question for just plugging in directly to the function. Okay, so here we see examples of that. A factor x minus 1s go away, you'd be left with x plus 2, in which case, yes, we can plug a 1 into that and get back a 3. Part B, slightly more complicated factoring, but nothing you can't handle. Here's my work factoring the numerator. Here's my work factoring the denominator. What they have in common is an x plus 2. If you get rid of that, okay, here's what's left. Can we plug a negative 2 into what's remaining and get back a real answer? Yes, that works for a limit. C, this one doesn't look factorable in the conventional sense, but it technically sort of is. If you wanted to think about this x minus 9 as factorable into difference of 2 squares, root x plus 3, root x minus 3. Another way to do it, in fact, what I kind of did with my work, I just noticed this radical up here often can be dealt with by bringing in a conjugate. Or in other words, if I see 3 minus root x, if I choose to multiply 3 plus root x, top and bottom, okay, then I'm going to get some nice cancellation. That's because the top, when you multiply this together, turns into 9 minus x, which is essentially x minus 9 just multiplied by negative 1. So I'm canceling out the x minus 9 and getting a negative 1 there. What remains here, you can plug in your 9 and get back an answer. D, the answer, this one does not exist. This comes up a lot where you have an absolute value in either the top or bottom. Okay, this is a good one to be able to graph. They're really easy to graph, and a quick picture, a visual, will make you understand that these questions are not that bad. It basically says, if x is greater than negative 2, the top and the bottom will always be the same. And anytime you have a number over itself, the value is just 1. So that's why I'm drawing a horizontal line with a value of 1 to the right of x equals negative 2. If x is less than negative 2, well, the top is positive, the bottom will be negative. But other than that, the values are the same. So, that turns into -1. And of course, I got open circles on both of these pieces because of the fact that you can't actually plug in a -2. Long story short, if you graph that, you can see that limit from the left is -1, limit from the right is +1. Overall does not exist. All right, we're almost done here. A couple quick things. I'm hoping your teacher last year shared this limit with you. Later on in the year, we'll explore this in more detail as to why it is what it is, but this is a good one for now to at least just have memorized. Okay, and then there's one example that shows you how you might use this information to help you solve some slightly more complicated looking limits. I'm breaking this thing up using the same properties from earlier. Okay, 2 times the limit of sine x over x minus the limit of, what I did here was I'm making this 3x squared over x, which simplifies to 3x. And then you go from there. All right, if you have any questions about what you saw, make sure you ask me in class or shoot me an email. Yeah, that's it for the first video. Thanks for watching.